Here's one that has a lot of symmetries. I can tell that this graph has let's see, origin symmetry, because whether you give it r or minus r, because of the way it's set up here with this r squared, if r theta satisfies the equation, so will negative r theta. That's a condition. Do you see why? Because either way, it's going to take it and square it. If you square r or you square negative r, you still get the same value. So that means this graph has to have origin symmetry. Also, because it has theta is only involved in this sign, and because we saw that the sine of pi minus theta is the same thing as the sine of theta, we know that if r theta satisfies the graph, then so does r pi minus theta. Now pi minus theta, r pi minus theta is just on the other side of the y-axis, so we know that this graph is going to have y-axis symmetry. And what's interesting is if a graph has origin symmetry, if you can rotate it 180 degrees and it looks the same, and you can flip it around the y-axis and it looks the same, then you can actually flip it around the x-axis. So if you have these two, well, if you have these two, origin and y-axis symmetry, you're guaranteed to have the third one, the x-axis symmetry. So this is going to have a lot of symmetries in it when we look at it. And we can just tell that from the way it treats certain points. Now, if it doesn't, the problem with polar is always that points have multiple representations. So symmetries can have more than just the ones more than just these representations that we've discussed. So just because it fails one of the three tests that we've looked at doesn't mean it doesn't have any symmetries. It may still, but if it passes one of those tests, if you can see that it has that property, then you know that the symmetry is there, and that's kind of worth knowing. Okay, let's look at this. R equals the sine of theta. Now that's not in r squared equals sine of theta. That's not in the form r equals some function of theta. But we can put it in that form if we solve for r. R is going to have to be either the square root of sine theta, or it could be negative square root of sine theta. So I'm just solving for r. So to graph this function, we're actually graphing, I'm going to graph two functions in one. So let's start off by thinking about the graph of sine theta. Sine theta, if this is 2 pi here, and this is pi, and here's pi halves, and halfway between pi and 2 pi will be 3 pi halves. Sine theta starts at 0, goes to 1, goes back to 0, down to negative 1, and back to 0. That's what sine theta looks like, right? Now we're going to need to take the square root of sine theta, and that means that we're not going to see anything in this range. Sine is negative here, and so you've got to take the square root, you get something complex. But if we take the square root of these positive ones, we can do that. So, and all we said was that the square root of a small number, a number between 0 and 1, is actually going to get bigger. So this is going to be the graph of sine, just kind of plumped up a little bit. Every number gets a little bit longer. So for example, at pi thirds, what would be a good one? Yeah, at pi thirds, or pi 6, sorry, at pi 6, the sine is 1/2, so the square root of 1/2 is 1 over root 2, it's about 0.7, so it's just taller than it normally would be. Instead of being at 1/2 at pi 6, it's a little bit higher. Okay, so we have that graph. Now at the same time we can graph this other one too. Well, we can come back to that. Let's graph the upper half first. So we're just working on graphing this piece of it, the square root sine theta. You see, as we turn, this would be east to north to west. We're at the origin. When we're facing north, we can walk out a distance of, when we're facing east, we're at the origin. When we're facing north, as we turn to face north, we can walk out further and further and further. When we're facing north, we can actually take a full step out. And then by the time we're facing west, we're back at the origin again. So we're going to get some kind of loop. Now we could fill in maybe a few more details. Let's see. When we're facing pi fourths, which would be northeast, then the sine would be root 2 over 2, which is about 0.7. So we take the square root of that. Ooh, let's see. That's going to be, well, more than 0.7, huh? So almost about 0.8, I would guess. So when we're facing northwest, it's about 0.8. Same thing when we're facing northeast. When we're facing northwest, because of the symmetry here, we have the same value. So we have about 0.8 when we're facing northwest. So you can see we make kind of a big loop here in the graph. That's one possibility. It came from solving this equation for r. That's one possibility for r. But we have this other function to graph. Notice that it's just negative square root of sine theta. So if this is the graph of square root of sine theta, the other one is just this graph flipped. So we have this. So as we in the second one, as we turn from east to north to west, we're looking out into the first and second quadrants, right? But we're walking backwards. So instead of walking forwards with a positive radius, we walk backwards. It's going to create this loop here. So let's see, we've got a couple points that I can put on here. So we're facing this direction, right? We're turning this direction, but we're walking backwards. And so it creates this loop down here. Okay, so there's the graph, what we've got. Now I actually graphed it. Oh, all right, so you can see that it grew a little faster. I was thinking of, just remember that the square roots of small numbers actually get bigger, and that's what's sort of plumping out the leaves here in this graph. So just to review, we had three different kinds of symmetries. We know how to draw a graph, right? We think if we have r as a function of theta, first we graph it in r theta space, so theta on this axis, r on that axis, and then we use that, we interpret each point on that graph as giving us a direction to face. Right? That's the angle theta, and this point gives us a distance to walk. So if the radius is negative, we could be facing some direction, but we'd actually walk backwards. That's how we get the graph. And then we've gone over examples where we can see that the function, if the function can't tell the difference between the point r theta and the point r negative theta, or if it can't tell the difference between r theta and negative r pi minus theta, you know it's going to have x-axis symmetry. It might still have x-axis symmetry if it can tell the difference between these two. That's because there are other ways of characterizing the same point in polar. Here's the test for symmetry about the y-axis and the test for symmetry about the origin. So we can see those symmetries. We know how to draw the graphs. We're pretty good.